Hey guys, today in microcontrollers we are gonna discuss about the topic arithmetic operations and their impact on status flags. Arithmetic and logical operations. The ALU is the core of the computer. It performs arithmetic and logic operations on data that do not realize the goals of various applications. Example scientific and engineering programs, but also manipulates the address. Example pointer arithmetic. In this section, we will overview the algorithms used for basic arithmetic and logical operations. A key assumption in the 2's complement representation will be employed unless or otherwise noted. Boolean addition. When adding two numbers, if the sum of the digits in a given position equals or exceeds the modulus, then a carry is propagated. For example, in Boolean addition, if two ones are added, the sum of the obviously 2 base 10, which exceeds the modulus of 2 for Boolean numbers. B equals Z is equal to 0, 1. The integers modulate to 2. Thus, we record a 0 for the sum and propagate a carry valued at 1 into the next more significant digit as shown in the figure. Here 5, 10 and 6, 10, when 0, 1, 0, 1 and 0, 1, 1, 0 are added, we get the answer as 1, 0, 1, 1. So in order to get this, here we can see that 0 and 1 gives us 1, 0 plus 1 gives us 1, 1 plus 1 gives us 0 with 1 carried to the next 0 and 0, which gives us 1. Thus, in this problem, we do have carries, and this should be taken into consideration because it plays an important role. Boolean subtraction. When subtracting two numbers, two alternatives present themselves. First one can formulate a subtraction algorithm which is distinct from addition. Second one can negate the subtrahend. That is, in a minus b, the subtrahend is b. Then performs addition. Since we already know how to perform addition as well as 2's complement negation, the second alternative is more practical. Figure 3.2 illustrates both processes using the decimal subtraction 12 minus 5 equals 7 as an example. Just as we have a carry in addition, the subtraction of Boolean numbers uses a borrow. For example, in figure 3.2a, in the first least significant digit position, the difference is 0 minus 1 in the ones place is realized by borrowing a 1 from 2's complements, 2's place, next more significant digit. The borrow is propagated upward towards the most significant digit is zeroed. That is until we encounter a difference 1 minus 0. In the figure we can see that we have subtracted 12 minus 5 which gives us 7. We have taken 1 1 0 0 and 0 1 0 1. Thus we get 0 1 1 1. Here in this case instead of a carry we get borrow as the main thing and it should be considered. This is an example of Boolean subtraction using unsigned binary representation and even the addition of 2's complement with negation or a negative symbol. Overflow. Overflow occurs when there is insufficient bits in a binary number representation to portray the result of an arithmetic operation. Overflow occurs because computer arithmetic is not closed with respect to addition, subtraction, multiplication or division. Overflow cannot occur in addition subtraction if the operands have different respective identical symbols. To detect and compensate for overflow, one needs n plus 1 bits if an n-bit number representation is employed. For example, in a 32-bit arithmetic, 33 bits are required to detect or compensate the overflow. This can be implemented in addition by letting a carry, borrow, occur into form the sign bit. To make a pictorial example for the convenience size, figure 3.3 illustrates the four possible sign combination differencing 7 and 6 using a number representation that is 4-bit, that is can represent integers in the interval minus 8, 7. In overflow, it's like extra carry or a borrow is added. Example 7 plus 6 we get 13. So we have taken the binary digits 0, 1, 1, 1 and 0, 1, 1, 0 and we have added. Thus there is a borrow at 1 and 1 and 0 and 0. Even there is the negative symbol associated with them, we get the negative symbol itself. Logical operations. Logical operations apply to the fields of bits within a 32-bit word, such as bytes or bit fields in C as discussed in the next program. These operations include shift left and shift right operation, as well as bitwise and or, in which and I or I is used. As we saw in section 2, bitwise operation treat an operand as a vector of bits and operate on each bit position. C-bit fields are used, for example, in the programming communication hardware where manipulation of a bit stream is required. In figure 3.5 is represented C code for an example communication routine where a structural is called receiver is formed from an 8-bit field called receive byte and two 1-bits field called ready and enable. This sets the receiver ready to 0 and receiver enabled to 1. Note how to MIPS implement the functional of the code where the state of the registers is S0 and S1 is illustrated in the 5 lines of the diagram register contents below the code. In particular, the initial register state is shown in the first 2 lines. The S2 instruction loads the content of the S1, the receiver, into S0, the data register, and the result is shown in the second line of the register contents. Next, the SR1 instruction left shift from S0 24 bits, thereby discarding the enable and ready field information, leaving just the receiving byte. To signal the receiver that the data transfer is completed, the AND I or the OR I instruction are used to set the enable and ready the bits of S1 which corresponds to the receiver. The data is S0 that has already been received and put in a register, so there is no need for its further manipulation. Full adder. Now let us consider that one bit recalling the carry situation shown in the figure 3.1. We show in 3.7 that there are two types of carries, carry in that occurs in the input and carry out at the output. Thus in the diagram we can see how this works with the carry in the carry in and the carry out. Here in each bit of addition has three input bits AI, BI and carry LNI as well as two output bits sum I carry out I where carry in I plus 1 equals carry out I. Note the I subscript denotes the ith bit. The relationship can be seen when considering the full adder's truth table as shown. Conclusion. In conclusion, this presentation has explored the arithmetic operation and their impact on the status flags. Understanding these concepts is crucial for effective program design, debugging and optimization. By mastering the interplay between arithmetic operation and status flags, developers can enhance the performance and reliability of their systems. Thank you.